Imagine a star dying. You probably picture a light simply winking out, its fire extinguished, leaving behind only cold, silent darkness. But what if some stars refuse to go quietly into that good night? What if their death was not an end, but the start of a 1,000-year-long light show? In our universe, there are ghosts, celestial remnants of stars that exploded long ago, yet their light still blazes across the cosmos, reaching our telescopes today. This is not spirits or magic. It is physics pushed to the edge of belief. A star that is, for all intents and purposes, dead, yet shines with ferocious intensity. How can something that ended its life still be one of the most brilliant objects in our sky? That is the cosmic paradox we explore. This challenges our simple definitions of life and death. On Earth, an ending is usually final. A flame goes out and the heat is gone. A heart stops beating and the energy of life dissipates. But the universe plays by much grander, stranger rules. To understand how a dead star can still shine, we must first understand how a massive star dies. A star is not a static ball of fire. It is a dynamic engine in a lifelong battle between outward pressure and inward gravity. For eons, it fuses lighter elements into heavier ones, releasing pressure that balances gravity, a colossal, delicate equilibrium. But this process cannot last forever. When a star at least 8 times the mass of our sun exhausts its core fuel, gravity wins. The iron core collapses in a fraction of a second, triggering a shockwave of unimaginable power. Outer layers are blown away in a titanic explosion, a Type 2 supernova. For weeks, one star can outshine its host galaxy, releasing more energy than our sun will in 10 billion years. Supernovae are destructive and profoundly creative, forging elements heavier than iron and scattering them across space. Every atom of gold in a ring, every bit of silver in a coin was born in a supernova long ago. These elements enrich the interstellar medium, seeding new stars, planets, life. But what about the core that started it all? Depending on mass, it collapses into a black hole, or, halted by quantum mechanics, becomes a neutron star. Our prime example, the star that shines beyond its grave, sits 6,500 light-years away in Taurus. We call its remnant the Crab Nebula. More than a pretty picture, it is a historical event, a cosmic crime scene, with witnesses who left clues. In 1054 CE, skywatchers recorded a sudden guest star, visible by day for 23 days, by night for nearly 2 years. Centuries later, John Bevis found a faint cloud in Taurus. Charles Messier, comet hunting, cataloged it as M1. A 72-inch telescope sketched claw-like filaments. The name stuck. By the 1900s, photographs years apart showed the cloud expanding. Tracing the expansion backward pointed to the early 1100s, tantalizingly close to 1054. Accounting for acceleration refined the date, aligning with the 1054 guest star. The case was closed. The crab is the glowing debris of that supernova, the spectacular death of a massive star. Its direct link to human records makes it one of the most studied objects in the sky. If the explosion happened in 1054, why is the crab still bright? The initial blast faded in 2 years. The heat should be long gone. In 1968, astronomers detected clockwork pulses, once every 33 milliseconds. At the heart, a neutron star spinning 30 times per second, the crab pulsar, the collapsed core itself. Imagine more mass than the sun crushed into a city-sized sphere. A teaspoon would weigh billions of tons. As the core collapsed, it spun faster. Conservation of angular momentum. Its magnetic field was squeezed to stupendous strength. A hypermagnetic dynamo. Misaligned magnetic poles sweep beams through space. When they cross Earth, we see pulses, 30 each second. A constant torrent of energy from the pulsar powers the entire nebula. The star is dead, but its heart still beats. The pulsar slowly spins down. The lost rotational energy almost perfectly matches the nebula's radiated power. The smoking gun. Every glowing tendril is lit by the fading spin of the tiny, mighty engine at its heart. Loving this cosmic detective story? Tap like, share with a space lover, and subscribe so you never miss our next deep dive. The pulsar's raw energy must be converted into the visible light we see, painting the crab's haunting beauty. A pulsar wind, torrents of charged particles moving near light speed, slams into the supernova debris, raising shockwaves. The inner ghostly glow is not heat, it is synchrotron radiation. Like in Earth's particle accelerators, ultra-fast electrons spiral through magnetic fields and radiate across the spectrum. This emission spans radio to gamma rays, with the visible inner glow a sign of relentless power. The outer reddish filaments, hydrogen, helium, oxygen, sulfur, shine from atoms excited by shocks and radiation, then emitting at specific colors. Two lighting mechanisms, one iconic look, a smooth synchrotron core, and the star's guts lit like a cosmic neon sign. By decoding colors and spectra, astronomers map composition, temperature, and magnetic strength. The crab is a sprawling physics lab in the sky, a stellar death revealed in multicolored detail. Multiple cultures recorded the 1054 supernova. Song Dynasty records note its date, position near Zeta Tauri, and a 653-day fade. These observations are scientific data, anchoring brightness and refining supernova models. A debated petroglyph in New Mexico may depict the moon with the supernova on July 5, 1054, a tantalizing possibility. Rarely in astronomy can we see change over years. The crab expands about 1,500 kilometers, growth you can measure. Near the pulsar, wisps ripple at half-light speed, a cosmic weather system in motion. This slow-motion movie tests our ideas of pulsars and remnants. The universe is dynamic, violent, and beautiful. Echoes of 1054 still reverberate, and we can watch them from our distant perch. Elements in the neutron star imply a 9/11 solar mass progenitor, yet the 1054 explosion seems under-energetic. Why a whimper, not a bang? In the last decade, the crab has erupted with mysterious gamma-ray flares, brightening by factors of 5, then fading. They seem near the pulsar, but the mechanism is unknown. We do not fully understand how the wind is launched, nor how it so efficiently energizes particles for synchrotron light. Wisps and jets are clues, but they reveal tangled shocks and magnetic turbulence still being deciphered. It's like watching a hurricane's surface. Dramatic waves above, hidden currents below. The intricate web is organized. Does it encode the progenitor's rotation or magnetic field just before the blast? The crab is a cornerstone of astrophysics, the first supernova remnant tied to historical records. Its pulsar confirmed neutron stars, opening studies of matter at extreme density and tests of general relativity. Bright and stable, it's a standard candle for high-energy astronomy, a reliable cosmic beacon. By tracing its filaments, we see oxygen, carbon, iron, raw material for future worlds. We are made of stardust. A death 6,500 light-years away is part of the grand story that led to us. A star died a millennium ago, yet its ghost shines on. The light we see is freshly made, powered by a tiny, crushed, spinning heart. In the universe, endings are transitions. Mass becomes spin. Spin becomes wind. Wind becomes radiant light. Over tens of thousands of years, the pulsar will slow, the wind will falter, and the synchrotron glow will fade. For now, the crab remains a shining monument to a deeper truth. Even in death, there can be glorious, brilliant light. What amazed you most about the crab's 1,000-year light show? Comment below, and if you enjoyed this, please like, share, and subscribe for more journeys into the cosmos.